In this video, I reintroduce to you conic sections, something you've seen before in pre-calc. So this video will go pretty quickly. A conic is generated by intersecting different lines at a common point and then revolving one of the lines about the other while keeping the angle between the lines constant. It gives you a shape kind of like this. Now if you want to know a conic section, it just means take that object and then intersect it with a plane. Now if you get a non-trivial intersection, like don't go right through the point where the two cones meet, don't go along the edge to get a line. If you get a non-trivial intersection, you get what's called the conic sections. The other ones, the point, the line, the two intersecting lines is actually possible. Those are called the degenerate conic sections. While that's the definition, it's not terribly useful in order to derive things. So an equivalent definition is in terms of distances. The conic sections, at least the non-degenerate ones, is the set of all points in a plane that satisfy one of these properties. If it's a fixed distance from a single point in a plane, that's called a circle. If it's equidistant from a fixed point and a given fixed line in that plane, it's called a parabola. If the distance between two fixed points in that plane is a constant sum, then that's called an ellipse. And if you have the distances between two fixed points in the plane have a constant difference, that's called a hyperbola. I'll derive the formula for you quickly. Let's look at the set of all points equally distant from a fixed point called a focus. In this case, that's the point 0, P, and a given fixed line called the directrix. Now the point that's directly in between the focus and the directrix, that's called the vertex. That is a point on the graph. In order to make our equation nice, we're going to assume that we move the axis system so that the vertex is at the origin and going upwards is going through the focus. So then the focus would have coordinates 0, P, where right now P is positive. X, Y would just be some other point on the parabola. Now the distance between that point and the focus is the same as the distance from the point to the directrix. That's why this distance here is the same as this distance here. Well then, because I know the coordinates of this point on the parabola, it's X, Y, I can find the coordinates of this point on the directrix. Because if the distance between the vertex and the focus is P, the distance from the vertex to the directrix is also P, so this equation then being below the x-axis must be y equals negative P. So the y coordinate of this point that's directly below our point on the parabola has to be negative P, and it has to have the same x coordinate. Because of that, now I can compare the distances by looking at the distances between these two different points and then between these two different points. So doing so, I would have that formula. That then is the distance between these 2 points, that's the square root, and then this distance is just a vertical change, so I just take the difference in the y coordinates. Then I square both sides. After I get rid of the x equals 0 to be x, and I square everything out, you get that. You then can see there's a whole lot of terms that cancel. The y squares are the same, the p squares are the same on both sides. Canceling all that and bring everything to one side gives you that equation. That is the standard form of the parabola. This is why way back when you were taught y equals x squared is a parabola, it's because it has this form where p is 1/4. Now, if you want a more general version, if you want the vertex to not be at the origin, you just shift the x and the y coordinates to be where the vertex is. So h, k here would be the vertex in both of these formulas. Also, I assume that the parabola went upwards. It could go downwards if p is negative. It can also go right or left if the roles of x and y are swapped. These are then the formulas for a horizontal directrix or a vertical directrix. And where in the first one, notice that p is multiplied to y, and p will actually change y values because you go from the vertex up or down, depending upon whether p is positive or negative, to get to the focus. In the other case, though, the p is multiplied to x. That means that p will affect x values. That means then your parabola, its focus will be to the right or to the left, and therefore the parabola opens to the right or the left. I'll do an example. Let's find the equation of the parabola with directrix x equals negative 2, and whose focus is 6, 3. So you have your line, where the line would then be x equals negative 2, and then you'd have a point where that point would be 6, 3, and that's the focus. Well, directly between these two would have to be your vertex. Well, that would then mean, since going left and right, the y value here would have to be the same as here. It'd be 3, and the x-coordinate is -2. That'd be -2, 3. That's the point. That's the projection of the focus directly down upon the directrix. That means I can easily find the coordinates of the vertex. It's just the midpoint of these two. So that midpoint would then be, take the -2, add the 6 to get 4, and divide by 2. That would then give you 2, 3. That's the h in the formula, which is 2, and that's the k in the formula, which is 3. Next, I need to know what the p is and what it changes. P is the directed distance going from the vertex to the focus. So that's going this way. That means p must be positive, and p here is 4. Notice also that p is changing x values. Because of that, I know the general formula. It has to be 4p times x minus h, because the p's multiply the x, changing x values. And the other side has to be y minus k squared, and they're equal. I just plug in numbers now. So you have y minus 3 squared is equal to 4 times p, which is 4, times x minus h, which is 2. So you have y minus 3 squared is equal to 16 times x minus 2. That's the equation of that parabola. The next conic section is called the ellipse. It's the set of all points whose distances from two fixed points, called foci, in the plane is a constant sum. Now I've drawn a picture to show you, get an idea what it looks like. Some definitions we need for the ellipse would be that the line going through the foci of that ellipse is called the ellipse's focal axis. The midpoint of the foci is called the center, and the points where the focal axis intersects the ellipse, those are called vertices. Then we often call the major axis to be the segment connecting the vertices, and then the minor axis is perpendicular to the major axis, and it passes through the center. So then it goes between two different points on the ellipse. Now, if you look at the major axis and the minor axis, we will say that the length of the major axis is 2 times a number a. The length of the minor axis will then be declared to be 2 times some number b, and the distance between the foci will be called 2 times a c, as you see right here. That means we then have distances from the center to any of these major points. But if you look at the ellipse, you should notice that if you go from the focus to the vertex back to another focus, you can think of that as two different distances. The distance from the focus to the center, which is a, and then the center to the vertex, that's c. So that's a plus c so far. And then you add, it's the difference in the distances between the center and the vertex and the focus and the vertex. So that difference has to be a minus c. So that constant distance that forms the actual ellipse is a plus c plus a minus c. It's 2 times a. So the major axis length is 2a, but that's also that constant distance that's formed, that's used to form the ellipse in the first case. Now that's useful to know, because if you go back and look at the picture again, but this time look at not the vertices, but go from the foci to the points that are on that minor axis. We'll just pick the top one. Now looking at symmetry, since the ellipse here has to be perfectly symmetrical in terms of the x and y axis, that means that both of these line segments you see have to be the same length. The whole length though has to be 2 times a. So the length of that one side is a. But the distance between the center and the foci is c. And the distance between the center and that other point is b. That makes a right triangle. So we have a way to relate them. You have b squared plus c squared equals a squared. I know it'd be nice if it wasn't that way, but that's the way it is. The way I like to remember it is I remember a squared and b squared. A in the ellipse is larger than c. So I want to take a squared minus c squared. That's a positive number. It happens to equal b squared. I've already derived one formula for the parabola. Now I'll derive the standard form for the ellipse. I'll assume that the center is at the origin and then the major axis lies along the x-axis. That means the foci have to stand at plus or minus c, 0. I'll pick some other point x, y on the ellipse. Now remember, the sum of the distances from the focus to this point and then back to the focus, that has to be a constant 2a. So here I am just writing down what I just said. Find those separate distances by using the distance formula for 2 points. To simplify that, as that actually is the equation of the ellipse, it's just awful looking. I'll simplify it by, let's get rid of the square roots. So I'll isolate a square root. I'll square both sides. There you go. That's what it would become. Notice how there's a common y squared. I'll cancel those. On the left, I have an x plus c squared. On the right, I have an x minus c squared. I'll just multiply those out and then cancel all the terms. By doing so and bringing all the c's, I'd have a 2xc and a minus 2xc. I'd bring them all to one side. You get that equation. Then I will once again isolate the square root, doing so. Then I'll square both sides. When you square both sides, you get that. I'll then distribute the right-hand side square to get this big long mess. And on the left-hand side of this equation, I'll also distribute the a squared through the expression. Also at the same time, I'll take the x minus c and square it out. So you have this big long mess. Notice though, once again, there's a bunch of things that cancel. So I'll just cancel them. You have a minus 2cxa squared on both sides. Notice that you have a c squared x squared on the right-hand side. I'll subtract that. Notice that you have an a squared c squared. I'll subtract that. By doing so and combining terms, you get this. But I remember though that a squared minus c squared, that's b squared. So I get that. Then I divide both sides by a squared b squared. That's the standard formula. That is the standard formula for the ellipse, where the major axis is horizontal and it's centered at the origin. So this one slide then captures the main ideas. It shows you where the center would be, the vertices would be, the major axis, the minor axis, shows you the values A, B, and C and how they relate to the focus, the center, and so on. Also, I've chosen to give you the more standard formulas for where you have a horizontal major axis or a vertical one. Notice the only difference for the horizontal major axis, the a squared is underneath the x, while the vertical major axis, the a squared is under the y. Now for the ellipse, a squared is always bigger than y squared because of the fact that a squared is equal to b squared plus c squared. So a squared must be larger always. Also notice that in the equation for the horizontal major axis, the a squared is under the x squared, so the a affects the x. So a then changes x values. So from the center, you can get to the vertices by changing the x values. And looking at my picture, whatever a changes, c changes, and vice versa. For the vertical major axis, notice that a squared is under y squared. In that case, the a would change y coordinates of points. So from the center, you would go up and down to find the vertices. And since a and c would affect the same things, you would go up and down to find the focus. Also, I shifted the whole graph so the center is now at h comma k instead of the origin. In all cases though, don't forget b squared is equal to a squared minus c squared because a is more than c. So a squared minus c squared is positive, it is b squared. Let's go ahead and do a problem. I want to find the foci and sketch the graph, and along the way I'm going to verify that this thing here is an ellipse. To do that, I need to put it in one of the standard forms. So notice I have to write x minus something squared and y minus something squared. To do that here, I need to complete the square at least once. So for the very first term, I'll take x squared minus 2x, take this negative 2, have it to get negative 1, square it, and I'll add 1 on both sides right away. That way I can write this as x minus 1, that quantity squared, plus 4y squared, and that would then be equal to 16. By dividing by 16, I would get x minus 1, that quantity squared, over 16, plus y squared over 4. Notice I did not write 4 over 16. I made sure that this number is 1, and if there are any constants, they're here, and that equals 1. I know for the ellipse that a squared is more than b squared, so a squared has to be 16, b squared has got to be 4, and since I remember that a is more than c in the ellipse, you have a squared minus c squared is positive. That is what b squared is. B squared is 4, a squared is 16. So I have an equation I can solve for c squared. C squared is 12, so c is the square root of 12 plus or minus the square root of 3, and we use the positive here. So I can find the foci really easily. First, the center. The center, you have h minus k, or h comma k. The h here is 1. Remember, it's x minus h. So this is the opposite of h. So h is 1. And k is 0. So the center is at 1 comma 0. Since a squared is under x, a and c will both affect x values. So I can find the foci pretty easily too. Our foci are found by taking this point 1 comma 0, and to the x value I add and subtract this. So the foci are 1 plus or minus 2 square root of 3 comma 0. Now after that, the last step would be is how would you go about graphing it? So here is my Cartesian coordinate system, and I have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's probably good enough for me. The center is at 1 comma 0, and I might have to go down 1, 2, 3, and so on. To start from the center, I can find the vertices by going 4 in each direction. So I have to go 1, 2, 3 at least. So I have to go 1, 2, 3, 4. It's over here if I had drawn it the scale. It's over here if I had drawn it the scale. And then 1, 2, 3, 4. It's over here if I had drawn it the scale. And then the B here would be 2. So I go up to 1, 2, and I go down to 1, 2 to get these points. The ellipse looks like this, which is really difficult to do on my tablet because I have very little resistance. So that would be the ellipse if I had drawn it well. But you get the idea. The set of points whose distances from two fixed points in a plane is constant difference is just the last conic section called the hyperbola. And just like before with the ellipse, the line through the foci of a hyperbola is just called the hyperbola's focal axis. The midpoint of the foci are called the center, and the points where the focal axis intersects the hyperbola is called the vertices. This slide contains all the major features for a hyperbola. So A is still the distance from the center to the vertex. C is still the distance from the center to the foci. B is the distance also from the center to a point perpendicular to that focal axis, but that point is not something we call or talk about, as it's not actually a point on the hyperbola. But B is needed because A and B together make a box that you see here, and if you draw the diagonals and extend them out forever, they will pass through the center, and those lines are the asymptotes of this hyperbola. It's what your hyperbola will tend towards as you go off into the distance. So B is connected to the slope of those asymptotes. Now I've given you two different formulas depending upon whether you want a horizontal focal axis or a vertical one. Notice in each case the positive term comes first, and also in each case the a squared is always under the positive term, not the term that's being subtracted. In each case though, a squared for the horizontal focus axis, the a squared is under x squared, so a changes x values. So A and C change the same thing. They change x values. In the second case, the vertical focus axis, the a squared is under the y squared. So that means A changes y values. So then the A and the C will both change the same thing. So the vertices and the foci go up and down from the center. There's also a new difference. If you look at the pictures, see how C is larger than A. So C squared minus A squared is a positive thing, and that happens to be B squared. That's the one nice thing to remember about these two different shapes, the ellipse and the hyperbola. So as an example, let's find the equation of this hyperbola. Now if you think about it, looking at it, here is the x-axis. One of the foci is at -2, 0. Another one of the foci is at 2, 0. That means I know where the center is. It's actually at the origin. So I now know what the center is, and because of that, I know what h and k are. So h and k, that's the center. and that is 0, 0. Also, since I know where the foci is, that means I know that the A and C are both affecting x values because they affect the same thing. I know then C happens to be 2 because that's the distance from the center to the focus. So that means then that the A and C both affect x values. So the formula must be x minus h squared over a squared minus y minus k squared over b squared. That is 1. So I know what h and k are. The only thing I need to know now is what is a and b. Well, I know what c is. Well, but you also know a way to relate b and a and c together, because we also know that in the case of the ellipse, that the c, the distance to the foci from the center, is larger than the distance from the foci to the vertices. So that must be b squared. Alright, so if I can find any two of them, I can find the other. And I know what c is. C is 2. So I now know b squared is equal to 4 minus a squared. Alright, we made progress. The only thing I haven't used this yet. Well, but again, if you think about the picture, so then the hyperbola is going to look like this, because it has to open around the focus, and you have an asymptote right here. I need to know then, what's the slope of that line? Well, to find the slope of the line, you need the a value, that's right here, that's a, and you need to know the b value. So then this ratio, that's the slope of the line. So the slope of my asymptote is the change in y, b, over the change in x. In this case, that's a. Notice b over a, y over x, b over a. So we know the slope then, in at least in one of the cases, has to be 1 over the square root of 3. So I don't know what they are, but I know a has now got to equal the square root of 3 times b. So a squared must be 3 times b squared. Okay, let's just plug that in over here. So we have b squared is equal to 4 minus a squared, which is 3b squared. That means 4b squared has got to equal 4. That means b squared has to equal 1. I don't care what b is. The minute I know what b squared is, that's all I needed. Because I now know what a squared is. It's 3 times b squared. That's 3 times 1. That's 3. So the equation of this hyperbola has to be x squared over 1 squared. And then you'd have minus y squared over 3 equals 1. And clearly, don't leave it like this. Don't write x squared over 1. Just write x squared. That's the answer. Now this is a calculus course, and as such, you deserve to see something more than you would see in your pre-calc class. So let's discuss the reflective property of the parabola and actually explain why it is so. So let's take a parabola. So in this case, opening to the right, the general equation would be y squared equals 4px. And let's take a ray that will then come in parallel to the x-axis and have it strike the surface. I'd like to know in general where it should reflect to. It's actually pretty difficult to set up. I don't want to go and set it up the way I have it here. So instead what I'll do is I'll shift the graph a little bit. That way the focus is at the origin so that the trigonometry is a little bit easier. The algebra is worse, but the trigonometry is a little easier. Then, as that ray comes in and strikes the surface, it hits a point and reflects. Now we don't know where it's going to reflect to, but let's just connect the line from that point to the origin and look at the angle between the tangent line to the surface and the ray. That would be alpha. But then also look at the angle between the tangent line and the segment connecting the point and the origin. We'll call that beta. I want to prove to you that alpha and beta are the same thing. Now, put in some more other angles. We notice that the red and the blue lines make vertex angles. So then we have alpha and alpha. But then if you look at the two parallel lines, the x-axis and the blue line, you have a traversal, which is the orange line. That means that this angle theta has to be the same as that angle theta also. Now that's useful because I can then find the slope of the red line, and that's actually equal to the tangent of the angle alpha, because that's the definition of the angle of inclination. But that's the derivative of y in terms of x, and if you just take the equation, y squared equals 4p times x minus p, and take the derivative implicitly on both sides, you'll find that the derivative of y in terms of x is 2p over y. Also, obviously, since the p is positive and the y clearly would be positive because it's above the x-axis, that means that the angle must be acute. So we now know alpha is acute. Also, using the same kind of idea, we can find the tangent of theta because it happens to be the angle of inclination for the orange line. All we need is one point on that line, which is x comma y. So that would be y over x. So we now know what the tangent of theta is. And we now also know that alpha, that the theta is, at least in this picture right now, is going to be obtuse, but we don't actually care. Now, in order to show that alpha and beta are the same, let's now look at the tangent of beta. Well, beta though, looking at my picture, since theta is equal to alpha plus beta, that means that beta has to be theta minus alpha. So let's find the tangent of that difference of angles, which we have by the difference angles formula for tangent, this expression. But I know what the tangent of theta is, and I know what the tangent of alpha is. Let's just plug it in, and let's just do a lot of algebra. So here we go. Here's me plugging it all in. I'll then multiply the two fractions to cancel the common y's, since the y is not 0. And then I'll multiply all the way through both top and bottom by x times y. In the denominator, though, I won't distribute the y through. I'll just leave it as y times, and I'll multiply the rest of it by x. Then I'll use that since y squared equals 4p times x plus p, I know what y squared equals. I'll just plug it in. Now I'll distribute that numerator. When you do so, and cancel terms, you get that. Notice though there's a common term, a common factor of 2p in the summation in the numerator. But then we notice that we have a common factor of 2 pi in the numerator. So I'll take out that common factor, leaving me with x plus 2 pi as a common factor in the numerator and the denominator, canceling, giving us that the tangent of b is 2p over y. We know that y is positive, so now we know that angle beta is acute. But tangent of alpha and tangent of beta, they're the same number. They're both 2p over y. So since their tangents are the same and they're both acute, that means alpha equals beta. This means then that the parabola has a reflective property. If you ever have any source of energy that comes in parallel to the focal axis, all that energy will reflect off the parabola and be reflected right back to the focus. Anyone here who wants to test this thing, just go to the Franklin Institute and in Philadelphia. Up at the very top level, there is a very, very large room called the Sound and Light Room. Across from each other, about 50 yards apart, there's two really large dishes, which you can go and put your mouth at the focus of one of them, talk, even in a whisper. All that energy would then be channeled along its focal axis, and it actually is the same as the focal axis of the other dish at the other end, so that if a person puts their ear at the focus at the other dish, they'll be able to hear you like it's a phone call, and it doesn't matter how loud things are in the room. And that gives you a fairly basic introduction to conic sections. You've probably have seen all this before.